Welcome to Maths 420. We're now in chapter 2. We're going into what we call group characters. So as usual, we begin with definitions we need to understand the chapter. So there's the first part of the video. So as we continue, as we go through the weeks, more videos will be sent. Okay, so we have definition 2.1, which is the definition of character. So if you happen to have a matrix of this form, can be a matrix representation. Now you know what a representation is of a group G of degree M. So which means we have an M by M matrix here. Okay, the trace of AX, denoted trace AX. You know what trace is, isn't that? It's the sum of the diagonal from our very first video. Elements of the diagonal, okay? So the trace of the diagonal of our matrix representation AX is called the character of AX, meaning that this phi of x, that's the notation for the trace of ax, is this sum. Okay, so they are some of the elements, the diagonal elements, okay, of the matrix representation. That's what we mean by character. Okay. Next, you need to notice that if the characteristic polynomial of ax is considered, so if we're dealing with a characteristic polynomial, which can be denoted by this. So if you're looking for the characteristic polynomial of ax, we denote it this way. You can say lambda I minus ax, where ax is our matrix representation. Then the coefficient, this coefficient, lambda raised to power n minus 1, is equal to phi of x, which is all of the sum as usual, the characteristics of character of x, right? Okay, so basically just know them as notation. As we continue, you get to understand them more. Okay, now if you remember our bx, which was basically an extension of ax, remember, which we wrote as T inverse T, where T is our non-singular matrix, okay, is equivalent to ax, then they have the same characteristic polynomial. So once this bx and ax as equivalent, remember the definition of equivalent, okay, so once they are equivalent, then they have the same characteristic polynomial, meaning that this polynomial sum, this one, let me clean it so that you have a clearer screen, meaning that the polynomial phi of x with the diagonal sum, which is a11 plus a all the way to ann of that of ax, will be the same as the polynomial sum for that of bx, right? So you would have a11 ax plus all the way to amn, all will be equal to b11 ax, like that. So these sum will be the same. That's what it's saying here. They have the same polynomial sum. Okay, so let's continue. Another notation you need to know is that throughout this particular one, once we're dealing with a character of this matrix representation, our G is a finite group and its order is small letter g. So when you count the number of elements in it, you get G of it, and it's over the field K of complex numbers. Okay, and also once we are talking about ax and bx, its matrix representation will be of this form, and that of bx will be of this form, on the grounds that they are what? Not equivalent, as inequivalent reducible representations. So once they are not equivalent, then this is how we represent them. Okay, notice that our ij runs from 1 to f, meaning that our ax is an f by f matrix and our bx is a h by h matrix. That's why it stops at h. Okay, so just notations you need to know. Okay, so let's continue. We have what we call an inner product for functions of G. So what do we mean if we're told to define an inner product for functions of G? What we mean is that we have a characteristic function, a character of a of x, phi of x, and psi of x. These are two character functions on G. So we have two of them, this and this, with values in the field K. So that is to say that this phi of x is taking you to our field K, and so is psi of x. Okay, Then the inner product of the function, the inner product denoted this way, is this formula you see on the screen. Be careful with this x, it's not capital X, it's small letter x, okay? So this is the inner product for the function of g, okay? We also need you to note that this inner product is commutative. So even if I brought this in front of this so that you can flip the two sides, okay? That's what we mean by that. You can flip them, okay? So you can flip the sides, they mean the same thing. So the inner product is going to be 1 over g sum over x of phi of x times psi of x inverse, okay? Don't worry, just keep knowing the notation, seeing them. Note 1 over g is the order of our group G, remember? Okay, so that's where the G came from. The next definition you need to know is orthogonal functions. When you hear orthogonal, it means something is equal to 0, right? Okay, so the function phi of x and psi of x are orthogonal if this inner product is equal to 0, okay? The next you need to know is what we call a simple and compound characters. When do we have simple characters? The character of an irreducible representation is called a simple character, while the character of a reducible representation is called a compound character. Irreducible, simple. Reducible, compound. So once it is irreducible, it's that of an irreducible, we say it is what? Simple. If it is reducible, we say it is a compound character, okay? Now you know what a character is. It's simply the sum of the diagonal of the given matrix representation, okay? The next definition you need to know is what we call an alternative form of inner product. You know what an inner product is now. So the alternative is basically relating it with what we call the conjugacy class. Conjugacy class, for those in 419 and those in Math 306, those have done 306 I think, and 300, you will meet a little of the conjugacy. Well, dwelt more in 419, okay? Well, so when x lies in the conjugacy class, so when x is in this set, you can simply take your phi of x and note it as phi with subscript a, okay? And your psi of x, because x is in the conjugacy class, as this notation. And the psi of x inverse to be psi bar with subscript a, okay? Then the inner product of phi and psi we can define just as this. Now, you know this was a definition which we saw earlier, is that? Now, in place of all of this, the sum is over x and g, and we know that the number of elements in g is what? Is a g. Number of elements is small letter g, right? Okay, so we can write it as this: 1 over g, which remains as 1 over g, sum. Number of elements in g is this h raised to power a, okay? A representing the fact that it's in the conjugacy class, and then this phi of x, we know is now going to be phi subscript a, and the psi of x is now psi subscript a. Well, the inverse is psi bar subscript a, which is what we have over here. Again, where phi raised by a denotes the number of elements in the conjugacy class, okay? So that's what we have here on the screen. So this is another way of, an alternative way of defining the inner product. So whenever you see this definition, if this is written for the inner product, it's the same thing as this, okay? That's what we're meaning there. And we want you to note that if x lies in the conjugacy class, you can put the lambda x, oops, there's lambda, is chi of x to be equals to chi raised by a, and chi x inverse to be equals to chi bar raised by a, okay? So that's notations for you, okay? Now let's continue. It's just basically notations and definitions you need to know. Okay, so another set of definition you need to know for this in this chapter. Don't worry, everything you see us apply in the theorems and proofs and later on in the creation of the character table. Okay, so the character relations of the second kind is the next definition you need to know. So as a result of the form, this form here, now you know what this chi subscript I raised by A and chi bar raised by B represents, right? This because of this form, this G is the number of elements in the order of our group, is that? And then this HA is the number of elements in the conjugacy class. Then this delta subscript AB, delta could be 1 if it is in and 0 if it is not. Don't worry, all of this you will see us apply as you go into through the chapter. So like I was saying, so this definition here, because of this form, it is called the character relations of the second kind. So once you have this form, this thing we call to this, we say we have the character relation of the second kind. Okay. So what then is an induced character, which is the next definition you need to know? The character of the induced representation. Remember this induced representation I gave us as a class exercise. Okay, we were able to show that it was a representation, if you recall. Now, the character of the induced representation, this one, you're going to sum the diagonal, is called the induced character of phi. This, not his. This will be denoted as this. So whenever you're looking for the character of this induced representation, we just denote it by this. And this is it here. And it is a trace of AX, right? Which is the trace summing of the diagonal with entries of this form, which is just what you see here. Okay, so you need to know these definitions. Okay, the next is what we call a right transversal. So what are right transversals? Well, in 306 we saw that when you have a subgroup H of, say, of group G, that this H partitions the group G, right? And that we can write G in terms of the union of the subsets. Okay, for looking at the right cosets. Okay, so in this case you have HG union G1 all the way, combining everything together. Okay, well, let's continue with our definition. So when you have a right transversal, what we're simply saying is that if you have G to be written as a union of its right cosets, be a decomposition of G into right cosets of H, then T1, this T1T all the way to Tn are called right transversals of H in G. That's all. Note H is a subset or subgroup of G. Okay, so we now know what a right transversal is. Now we're going to a question. The question says, let AX be a matrix representation. You know what a matrix representation is already of G. Show that the character, this character of AX has the following properties. So we want to show that this character, you know what it is now, the sum of the diagonal entries of AX, the matrix there. We want to show that it satisfies this property. One, that equivalent representations have the same character. So if we have two equivalent representations, we want to show that they have the same character. If X and Y are conjugate in G, meaning that I can write Y, so G conjugates it, so that I have G, say X, G inverse, so conjugation, or it could be G inverse, X, G, depending on who the solution you choose and convenient for you, that if you have a conjugate in G, then the character of X and that of Y are the same. That's what we're told to do. Let's see the solution, shall we? So the solution says, let X and Y be equivalent representation. So they're equivalent. So we had seen earlier on that if they're equivalent, what happens? So let's read on. The equivalent representation means there exists an invertible matrix T such that T is written this way, right? With X in G. Then by the definition and property of character, so we know definition of character, right? It's the sum of the diagonal of AX and the diagonal of BX is what we're looking at. I want to make sure they're equivalent, right? We know that BX is going to be written thus, right? And AX have, so clearly they will have the same polynomial, character polynomial that we saw in the previous definition, just straightforward from the definition of character. Okay, so if that is the case, the sum of the diagonal for A is the same as the sum of the diagonal for B, the matrix, right? Thus, equivalent representations have the same character, and that's the end of the proof. Okay, basically you're just to show that once you have a representation that are equivalent, then the two characters, some of the character of the two are the same, and that's went directly by the definition of the property of the character of AX. Point 2, to prove the second one. The second one says, so we have conjugates, right? And I said you could have y to be equals to, say, G inverse X G, because that's what we mean by conjugate, where G is taken from capital G, right? So in this particular solution, we have used T, trying to meet up with the lecture notes you have. So we have, because of the conjugation, that y can be written as this. Okay, thus for any matrix representation AX, what happens? So if we happen to have AX, now we're saying y is this. So if AY, wherever we see y, we put T inverse XT, right? Yes, y is that. Y is this. So if you substitute that, you have this, since y is this, right? So AX equal to this becomes this. Why? Because A is a representation. Representation, remember, we said if once you have AXY, is same as AX times AY. I'm sure by now that has become part and parcel of you. You know this definition well. Okay, so because it's representation, it splits, right? So it splitted it, and so we have this. Okay, so we're now going to compare our knowledge of what happens to B. We know Bx is T inverse AXT, right? So if you compare what we have here and what we have here, you can see that this T inverse looks like this AT inverse, and this T here looks like our AT here, right? So we see that AX and BX are equivalent, are already equivalent representation, not B, but they are from our definition, right? So hence by 1, because they have equivalent representation, what happens to their traces? It means the trace of AX, AY is same as trace of AX, which implies that we have that the character are the same. The character of X and the character of Y are the same. So the steps to the proof of this second one is basically working almost like what we had done earlier on, but now we have used Y and given it its conjugation, right? And then we substituted, expanded here based on the fact that it is a representation, and then we compared our AT with BX, right? And then saw that, oh, AX and BX definitely will be equivalent representation because they are similar, right? And so by the solution of 1, we have this conclusion. Now, if you are given this in an exam and I didn't ask you to show 1, you have to prove how 1 came about, because I don't know what 1 is during exams. You will have to show it and write out the proof of it. Okay? The next question. So in the next question, we have that we have a matrix E, which is represented by entries in Z, and this is a H by F matrix. It's not a square matrix, right? And we're told that where the elements Z are from the field K, okay? We're told that if AX and BX, are in equivalent irreducible, they're not what equivalent, they are inequivalent irreducible representations, then we should construct a matrix C such that this happens. Now, I remember in our previous video we had seen something called Shor's lemma. Shor's lemma is going to be our guiding and basic foundation for this proof, because it is the only one that has something that has to do with something like this. I think T AX equal to AXT, if you can remember. AXT. Don't worry, we will see it being stated as we go. Okay, so because of that, we will want to relate the Shor's lemma and this proof here. And then we're told to find C. So we want to find that C, we want to construct C. We'll construct C based on the fact that we know that Shor's lemma is also linked to our matrix BX, which equals to T inverse AX T And if you remember, this was a matrix that had entries, if you remember. So we had Cx here, 0, and Ex, if I can recall here, and Dx here, right? And that manipulation led to a nice relationship between entries in Bx, such that we saw that Cxy was equal to Cx Cy, and Exy was equal to something big. And that led us to several proofs, if you recall. Now, with that as a background, and knowing that we are actually targeting Shor's lemma, we want to find C. Moreover, it's not just targeting Shor's lemma, but it's the only one that allows this kind of relationship all through the work thus far. Okay, so now in our solution, we set our E to be as it is, and let it satisfy all the conditions as stated in the statement of the question or theorem, as the case might be. And then we seek to construct a matrix C. And based on the knowledge of where we are going to fix our X, because that's what we did in the previous proofs of the theorem, it's going to be a language. And when we fix our X, we can set our Z to be something like this, Y times X. And noting that we can sum over X or sum over Y, and it's the same thing as summing over Z. It doesn't really affect it, right? Okay, so we also note that AX and BX are what? Inequivalent. They are not equivalent. They're inequivalent representations of degree F and H respectively. And recall our notation that we have this as our matrices at the beginning. So based on that, we will set our C to be this, defined as what you see here. I'm sure you'll be asking, how did you know, Ma, that this value C should be this? Well, like I said, we're working with Shor's lemma, and looking at Shor's lemma, we know there's something about it being satisfying the concept of BXC equals to CAX, and then relating it to our matrix for BX, which I had written T inverse AX, and the entries were particularly the only one that had other values in it. If you remember, I had a question mark earlier. So we're going to relate it with that. And with that knowledge, we want to see how, if I set or we set our C to be this value here, what will happen? So we set C to be the sum over Y, elements of Y in G, and B, Y inverse. There's an E here and a Y. Don't worry, as we continue, you will see why it actually turns out to be the best value for C. Let's see if that will be true. So again, we have fixed our X and we set our Z to be YX. So just manipulations, in your normal math indices, you have this. I could do this because I'm working with elements of a group. Okay, so now C is this value, right? Because wherever I see Y, what do we do? Let me go back a little. So we said C is this value here, right? So wherever we see Y inverse, what happens to our, because we set Z to be YX, right? So wherever there's Y inverse, the new value based on Y, Z being YX, we want to bring in Z and AY. Okay, so let's continue. So with that, if Z is this value and we're looking for B Z inverse AZ, what happens? You get something like this, right? Because wherever I see Z inverse, I plug in my value for Z inverse, which is, I didn't solve for Z inverse here. Well, you can solve for it and verify that this is what you get, okay, for Z inverse. And that of Z we saw is YX, right? Okay, so if that is the case, what happens to our next value? What happens here? How do we get this? You remember from, I think, 300 that whenever we have this, it becomes this here. This XY all inverse as Y, X all inverse. This will give me X inverse, Y inverse, right? You saw it in 306, okay? So that's how I got the two entries there. That's how we got this becoming this, okay? And this remains as it is, right? Don't forget the E is following quietly there, okay? Okay, so we know that B and AX are representations, so this opens up as you can see here. Agreed? The E remains as it is. And the fact that we can use associativity allows us to bring in, and then the sum is over what now? It's over Z, right? Okay, so we can bring in the sum and bring out X, okay? So we brought out BX inverse and brought in the sum BY inverse, and then there is AY inverse. Actually, I am able to do this because I had defined a C earlier, remember? What's my C? I defined it to be what you see right here in terms of Y, right? Okay, and I used my other definition here in terms of Z, right? Okay, so in the middle here, right here, you can see that this value is actually the one we had defined here earlier, our asterisk, right? So we plug in that C here. So remember this term C, everything here had C is equal here, C equal to this here. Okay, so again we now have C equal to everything here. Okay, our C is this one here. All of this is C, which is what I have written here. And then our new value, which is bx square, x inverse, and the terms in the block right here. And then there's ax. But I just told you that we've seen this before. Again, it was our C, which we defined in terms of y here. And we saw that if we fix x, the sum over x, or if we fix, the sum, it should be sum over y. Not x, but it should be y, because x is fixed, okay? So we're summing over y. That's why it wouldn't change anything. So we're summing over y, not x. Okay, so this now we know is C from that previous side, and this sum remains C because the sum over y in terms of y and sum in terms of z would not affect your representation. Okay, so let's see. Now we had proven this earlier. Is that? Check if you've not seen it. It's one of the previous videos. We're proving this identity. So we're able to see that this term bx inverse is going to be bx inverse is the same as bx all inverse, right? Okay, so that's what happened here, right here. Okay, this term remains there, the one that is our C, and ax is still there. So with that said, the C followed quietly, so you have C, this became bx, and this value C, right? The C at the beginning, and that's the C, and then we have here. So automatically we have gotten that C is equal to bx inverse CAX. So if I multiply on this side by bx in bx and this side too by bx, what happens? This goes to identity, so we have bx c equal to CAX, which is exactly what we wanted to prove. So truly our C is as created as we had earlier on. Okay, so let's continue. Okay, so with that we had finished proving proof for this particular question that we should construct a matrix C. I wish I'd even stated what the matrix would have been, C equal to something, okay? But you understand the body of the proof. Okay, so let's continue. Question 7 now. This is theorem 2.6, okay? It says show that if AX and BX are inequivalent irreducible representations, then every element of AX, when regarded as a function on G, is orthogonal to every element of BX. I want to show it is orthogonal to every element of BX. When did we say something was orthogonal? Remember, we saw the characteristic function. We said when it is equal to 0. If you remember those definitions, okay? So we want to show that this will happen. Wow, looks like a tall order, right? But anyway, let's see how we'll go about it. So the first thing we need to do is to make use of all that we've been showing the previous question we had solved, and we used the concept of Shor's lemma to guide us in the proof. Now, to show that this inner product will be orthogonal, to prove this, we construct a matrix. So first we have to construct a matrix. That's why that question came, okay? And the matrix arbitrary element of E of AX, and then we apply the matrix form of Shor's lemma. So let's go ahead and see. Okay, so now by the previous question, which was the one we saw the construction, what was our C? Our C was this, right? We constructed that, okay? And in the matrix and Shor's lemma, by Shor's lemma states what? Remember, I was trying to remember what Shor's lemma says, so this is what we have it to be. It says that let AX, BX be two irreducible representations of a K for group G, and suppose that there exists T, a matrix with coefficient K such that this happens. In our own case, in our construction, we saw AX equals to AX C. So in our own case is C, but in the definition in Shor's lemma, it's T that's used there. You could choose to make it C, but you have to change the notation here, okay? So that holds for all X and G. Then two things will happen if you have this kind of relationship. So we have the relationship and we're having two conditions, says Shor's lemma. It says that either T is equal to 0 or T is non-singular, so that this relationship holds, and that it will only hold on the grounds that A and B are what? Are equivalent. But what does our own question say? Our question says, does it say it is equivalent? Let's say. Our question says that B and X are inequivalent. So by Shor's lemma, first, we're able to construct this. We know how to construct it already by that lemma. So you should be able to state and construct that matrix during the exam or during the test. You must know how to construct this C. Otherwise, I'll ask you, how did you get it when I'm marking? To construct it, show that previous lemma during the exam or during the test, okay? So show how you constructed it and then apply Shor's lemma. Because once you construct it, it will satisfy this condition. And if it satisfies this condition, knowing that A and B are what? Are not equivalent, that is, they are inequivalent, it means that your C will be equal to 0. In this case, you can see T there, but because like I said, you can change your T to C, right? And to satisfy this condition. Yes, this one is AX, but remember, they are inequivalent. That's why we're having AX and BX. Note that, okay? Okay, so it means our C equal to 0 based on this, right? So let's go on. So since AX and BX are inequivalent, it follows that our C equal to 0. Whoa, what is C? You remember what our C was? It is this, which you have constructed or we have constructed. Okay, so C is this. Mathematically, you know this is a matrix which has this element, and E is a matrix which has this element, and so is A. is a matrix which has this element, right? So everything equal to 0 for all P and J, okay? So let's look carefully now. So it means that if this will be equal to 0, what happens? Now, E was chosen arbitrarily, right? And the equation is true, so the coefficient for each must be 0. Isn't so? So, meaning that all of this will be equal to 0 for all of these movements as we move the entries in our matrix. So if that is so, all of this equal to 0, it means our inner product, this inner product equals to 0 for all I, J, P, and Q, and this completes our proof. Okay, so again, our construction of C was arbitrarily done. Is that not so? Because we chose it in such a way that our matrix E, remember what E was? E was a matrix which was of the form Z, is it PJ or so? PQJ or so, PJ. Okay, so based on our choice of this matrix, It was chosen arbitrarily, and then we kept solving, and we ended up getting that by Shor's lemma C would be equal to 0, constructing our C. And then if this is equal to 0, and it means this sum equal to 0, our choice was arbitrary. And because it is arbitrarily done, it means our inner product, okay, will be in terms of B and A, because the E was arbitrarily chosen, okay? And hence, this inner product equals to 0, and the proof is complete, okay? Again, if you have questions, you can ask your question on the chat. It's possible I've not given you many information. I'm trying my best to unwrap the theorem to you as easily as possible. Okay, thank you. So again, go through the videos, know the definitions, key definitions you need to know, and slowly pause it, read through, try and understand it, ask your questions. Again, this is part 1. Other parts will be coming as we continue in the weeks ahead. Thank you.